Okay, so can you hear me? Hello. Oh, thank you. Okay, so yeah, let me start in 3 minutes. Do you have any question today? Okay, let me start today's lecture. Okay, this is the second lecture of the deep learning course. This is SeungryongKim. Today we're going to talk about the linear regression. Okay, so let's start. Can you hear me, right? Okay, thank you very much. Okay, so before starting, let's think about what regression is and what classification is. I guess most of you heard about these two kinds of concept, regression and classification. So here are very well-known examples of the regression and classification in computer vision field. As you can see here, from the single image here, the middle images represent the depth information. So I can say the depth information. The depth information means the relative distance for each pixel, which represent the each distance of each object. Another examples of classification is the semantic segmentation. Semantic segmentation here. So the main difference between the depth estimation and semantic segmentation is that the depth is the continuous value and semantic segmentation values the discrete value. So the objective of depth estimation to estimate the continuous depth values per each pixel, something like this pixel. And the objective of the semantic segmentation is to group the pixels that have the similar semantic meaning, such as the bed here or the wall here, something like that. So at the end of this course, we will implement these two kinds of the application, including the depth estimation and semantic segmentation. But today we will start with the linear regression problem. Okay, so let's continue. So here is the examples of the regression. What is the regression? What is the regression? So here's an example. So let's think about the problem of predicting housing price according to the size of the house. So here is the example. Okay, so these kinds of things that our training data set, each point represents the size of the house with the size of price. So we already have so many historical data between the size of a house and price of the house, right? So what we want to do is to predict the house price with respect to the size of the house, right? Then how can you do that? How can you do that? So this is the goal of the regression problem. Okay, so what is the regression? The regression is related to the input variable to the output variable to either predict the output for the new input, or to understand the impact of the input on the output. This is the two kinds of goal of the regression problem. So here is the example. So in this bottom figure here, this is the input variable defined as xn in the RT space. It means that the d-dimensional feature vector, and the output of the output yn is the output defined on the scalar space. So what we want to do is to find out the relationship between the input xn and output yn. So this is the goal of the machine learning, right? So in the regression problem, we want to find out the continuous mapping function between the xn and yn. So let's see the data set first. So to understand the regression problem, we have to define the data set first. So first of all, in regression, the data set consists of the pairs of the xn, the input variable, and yn, output variable, from the n is equal to 1 to the large N. Okay, so this is our training data set, or the training data, or the set of the data. So this is a formal representation of our training data set, where yn is the nth output, and xn is the vector of the t input, or the t vector representation. So this is the general form of our data set. And here, the number of pairs, or the number of training set, n here, n is the data set size, and in here, t represents the dimensionality of the input feature vector. Okay, so for example, our input xn represent as a t-dimensional vector. For example, something like xn1, xn2, blah blah blah, x and t in RT space. So it means that xn is the t-dimensional space, and yn is formally in the scalar space. Okay. So if we have the training data set consisting of the xn and yn, we can represent these kinds of things as a matrix form. Matrix form where we can represent each feature vector in row axis. So something like x1 1 comma x1 2 comma x 1 3 blah 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 x1 p with the scalar y1. So this is the first example. First training example. The second example is something like x21, x22, blah blah blah, x2t with the corresponding label y2. And then for nth variable or nth input variable, we can represent the input vector as a xn1, xn2, and xnt with n y. So this is the matrix representation of our regression data set. So here the low axis means the number of data set or the number of samples, and the x-axis represent the feature dimension with the label. Okay. So this is a formal representation of the data set for the regression problem. So in machine learning, the input variable, also known as a feature or covariate or the independent variable, explanatory variable or the exogenous variable or the predictor, something like that. And the output variable, also known as the target, label, response, output, dependent variable, measured variable, something like this. So this is the jargon for the regression task. So there are two goals of the regression problem. The first one is the prediction. Second one is the interpretation. So in prediction, we wish to predict the output for the new input vector. For example, what is the weight of the person who is the 170 centimeter tall? So in other words, we would like to predict the relationship between height and weight, right? So this is the first goal of the regression, to predict the relationship between input and output variable. The second goal is the interpretation. So we wish to understand the impact of the input on output. For example, taller people, heavier too. So in other words, we would like to interpret the relationship between height and weight, right? So in regression problem, we want to predict some relationship or the interpret some relationship. Okay, so here are some examples. What is the life expectancy of the person who has been smoking for 10 years? So in this case, is prediction or the interpretation? Prediction or interpretation. So this case means prediction case, right? Let's use the different prediction. The second one is does the smoking cause the cancer? Prediction or interpretation? This is interpretation, right? And there are many other examples, like when the number of the packs smokers smoke per day doubles, their lifespan gets cut in hertz, something like that. So let's please think about these kinds of things and doing yourself. So this is homework. So anyway, so there are two goals of regression problem. Okay, so then to find out to solve the regression problem, we need to find out the mapping function that approximate the output well enough given input data. So here's the things. So here xn is the input variable and yn is output variable. So and this f is this function f is our target, right? So our goal in regression problem is to find out this target mapping function, defined as f function, right? So here is the general procedure of the linear regression. So from the training set, something like xn, yn, from n is equal to 1 to large n, we want to find out the learning algorithm or the mapping regression optimization, which we will discuss later. But by finding out the learnable parameter in our mapping function, we can find out our target mapping function here. Then for the input variable xn, we can generate the output of this mapping function as a f of xn, right? Then we need to find out the mapping function that approximate this output to the real ground truth yn given input variable xn, right? So this is the mapping function of the regression problem. Okay, so before continuing, I would like to emphasize something. So actually, the regression is the regression find the correlation, not a causal relationship. So here is an example. This figure represents the relationship between the number of pilot and the number of the global average temperature, right? So as you can see here, it seems like there are some correlation between number of pilot and global average temperature, right? But you can easily imagine that it's not real, right? So it definitely be some coincidence, right? So when you think about the regression problem, you have to interpret your result with very caution. Okay, so it means that the correlation found by the regression model, it's not a causal relationship. Okay, so you have to keep in mind. So yeah, this was the regression. Then what is the linear regression problem? So this is today's topic, right? So what is the linear regression problem? So the linear regression is the model or the mapping function that assumes the linear relationship between input and output. Okay, let's think about the relationship of the height and width case. So as you can see here, some people have this height and this weight, right? Another person have the different height and different width, right? So from this kind of the training data, we want to find out the mapping function between height and width. Then there are several kinds of the possibility, right? But in linear regression case, we want to find out the linear mapping function represented by the this straight line, right? So in this case, in linear regression problem, we want to find out the straight line. So in straight line case, let's say height represented by the xn, width represented by yn, then the straight line can be represented by yn with some kind of the linear combination of the input variable. So for example, like x0 plus x1, w1 times x1. This is kind of the linear function, right? Then what is the nonlinear case? What is the nonlinear case? Okay, if we represent this straight line in a general form, we can represent this yn as a w0 plus w1 x1 w2 x2 blah 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 wt xt, something like that, right? Then in here, this is a linear combination, right? So that's why this formula, this equation called the linear equation. Then what is the nonlinear case? For example, something like the x1 times x2, or x1 square, or the square root of the x1, something like that. The equation that contain this nonlinear term, it's not a linear equation. It will be the nonlinear equation. So in linear regression problem, we want to find out the linear equation that approximate the input and output variable. So today we will start with this linear regression case. First of all, why do we learn about the linear regression? There are a lot of reasons. First of all, because this is a simple. Okay, let's emphasize. So this is simple, and this is easy to understand, and this is the most widely used, and it is the easily generalized nonlinear model. And most importantly, you can learn almost the whole fundamental concepts of the machine learning with a single linear regression. So as we discussed last week, actually this course is the deep learning. This is course for the deep learning, right? But to deeply understand the deep learning, we have to understand the machine learning first. So to understand the machine learning, you have to know, you have to understand this linear regression things, because in this linear regression, we can learn about the fundamentals of the machine learning or the deep learning, something like the cost function, optimization, or the gradient descent, something like that. So we have to start with the linear regression problem. Okay, so yeah, so let's continue. Is there any questions so far? Okay, so if not, let's continue. Okay, so let's think about the simple linear regression problem. So, okay, let's assume that there is only one input dimension. One input dimension means xn is also in the scalar space, yn is also in the scalar space. Okay, then we can get a simple linear regression function. Something like this. So yn is the output variable, and f is our mapping function, and xn is our input variable, right? Then this mapping function, this f mapping function, can be represented by the learnable parameter w here. So it will be represented like the fwxn. So in the simple linear regression case, this mapping function can be represented by the w0 plus w1 times x1. This is very simple case, right? Here, the learnable parameter w is consisting of the w0, w1 are the two parameter of the model, or the two parameter of our mapping function. Or mapping function. Our mapping function, they describe the f of w, fw of x. Okay, so let's go back to our previous example. So x-axis means the height, y-axis means the width, right? And we want to find out this straight line that represents this training distribution. So we can represent this straight line as this equation, right? So in here, this W0 represent the cross section of this straight line with the y-axis, right? Here. And this W1 represent the slope of this straight line, right? Here, right? So this straight line defined by the W0 and W1, right? So what we want to do is to find out the optimal W0 and W1 that will approximate the relationship between height and width. So in other words, this is the goal of this linear regression problem. Okay, so this is the representation of the simple linear regression. Okay, so what is the learning? Then what is the estimation? What is the fitting? Actually, these kinds of terms represent the similar meaning. So given the data, we would like to find out the optimal parameter W star. In our case, it was the W0 and W1, right? So what is the optimal parameter? What is the optimal parameter? Okay, if we have a time here, the goal of the learning is to find out the optimal. Okay, let's say optimal parameter W, right? So first of all, we have to define what is optimal. What optimal means in the linear regression problem. So actually, this process is called the learning, or the estimating the parameter, or the fitting the model, or the fitting the mapping function. Then the objective of the linear regression is to find out this linear equation parameter W that fit the model on our training data well. So then the question is how to find out this parameter. So to find out this parameter, we need to define the optimization algorithm. So today we will derive the cost function for this problem and the optimization method to solve this problem. Okay, so this is the general goal of the regression problem. Okay, so what is the cost function? Let's go back to the training set of our previous example. Okay, so in previous example, we wanted to find out the mapping function between from the input variable x to the output variable y, right? It is fwxn, right? So it was our mapping function. in linear regression problem. So first of all, let's consider the following model: simple linear model that have the W0 and W1 in the mapping function, right? So we want to find out this W0 and W1 that will approximate this ground truth data. So ground truth output, right? And this is the estimated output. Right? So in other words, how can we estimate or how can we guess the value of the W given the data? So intuitively, we have to find out the distance between the ground truth output and estimated output, and then find out the optimal W0 and W1 that minimizes this distance between ground truth output and estimated output. Okay, so let's see the disk example first. As we discussed previously, we have the linear mapping function here. So this is the estimated one, and this is the real ground truth label. So let's say we have a two training sample. For example, like 0, 0 and 2, 1. Okay. So let's say this is our training data. Then which values of the W0 and W1 represent well of this training data? So to answer this question, let's think about three kinds of the possible solution of the W0 and W1. So first of all, if we consider the W0 is going to be the 1.5 and W1 is going to be 0, then we can draw the straight line, something like this, right? So here is a 0, 1.5, and it should be parallel to the x-axis, right? Something like that. What about second one? When the W0 is equal to 0 and W1 is equal to 0.5. Okay, so first of all, it was something like 1 to 1 plus 0 times x, right? In second case, our mapping function should be 0 plus 0.5 times x, right? Then how can I draw this? This mapping function or this straight line should be something like this, right? Because when x is equal to 2, the output should be 1, right? What about the last one? When the W0 is equal to 1 and W1 is equal to 0.5, then our mapping function should be something like the 1 plus 0.5 x, right? Then how can I draw this? When x is equal to 0, the y should be 1, and when x is equal to 2, y should be what? 2, right? So right. Okay, so question. So which one is the best? Which reference function the best represent this training data? The middle one, right? So why the middle one is the best? Because if we think about the distance between the ground truth y and the estimated y, in the first case, the distance it looks like this. And second case, actually the distance is zero, right? Because they are exactly approximate the training data set. And the in third case, the distance is looks like this, right? So in this case, we can say that the middle one is the best because they have the smallest error between the ground truth and estimated one, right? So actually, this is the process of the learning. This is a learning process. We found the optimal parameter W that well represent the input and output relationship, right? So yeah, this is learning, right? But is this the optimal way? Actually not. Why? Actually, this is very brute force. Why? Because there are 100 or the 1,000 were the infinitely many possible combination of the W0 and W1. So it's not possible to search the every possible combination W0 and W1. So it is really hard to, actually it is impossible to find the optimal parameter W using such kind of the technique, right? So we need a more clever way to solve this problem. We will discuss this one later, but here is the intuition of the cost function. Okay, so what is the cost function? Actually, we already talked about this one in previously, but let's define the cost function in a systematic way. So idea is here. So the learning of the linear regression is to choose the best parameter W so that the fw of x is close to y. Actually, it means the distance between the ground truth one and estimated one for our training data set. So here's the idea. So yeah, let's see this page. So if we define the mapping function, something like this, we can measure the error between the ground truth one and estimated one. We can define this difference as a En, which is the error of the n sample, right? Then we can aggregate this error for each samples, something like this one, right? So because this is the first sample and this is the second sample, something like this. Then each samples have their own error, something like this, right? Then we can summation of this error for each samples. Here, this one, something like this, right? In this case, let's think about the least scale or the scale of the difference here. We aggregate this difference from the n is equal to 1 to the large n and divide by the number of data, right? So we can define this function to represent our errors when we define our mapping function with a W here, right? So the question is, which W values make this term as a minimum? So this is the goal of our training. In other words, the question is how to find the W that minimize this cost function, this function, right? So actually, we can generalize this equation as something like this. we can introduce the L of W. So the function of the learner parameter W. Then we can define the cost function here. So the cost function means the cost function defined by the estimated output and the ground truth output. So in here, this term is called the cost function, and our goal is to find the optimal parameter W that minimizes this loss function or this cost function. So this process is called the optimization process. Okay. So this is a general terminology in the machine learning. So to summarize, we have to define the cost function first, and then we have to minimize this cost function in terms of the learnable parameter W. And when we arrive the minimum point, we can say that this parameter W is the optimal parameter. Then that optimal parameter represents our final mapping function, which will be used in the testing time. Okay, so this is a general idea of the cost function. Is there any questions so far? Okay, so let's continue. Okay, so let's continue. Okay, so formally, the cost function, actually, it is also called the energy function or the loss function or the training objective, is used to learn the parameter W on it. The parameter in our mapping function W that explain the data well. That explain the training data well. Training data well. So in other words, our cost function quantifies how well our model explain the data or explain the training data. Or in other words, how costly our mistakes are, or how costly our errors are. So this is the definition of the cost function. Okay, so let's see the example. So to summarize, we define the linear mapping function, something like this, right? And we already know there are two learnable parameters, W0 and W1. And given the training data set, Xn and Yn, we define the cost function, define the distance between the ground truth Yn and estimated one using some kinds of the distance function, in this case, the L2 norm. Then we can aggregate this distance across the whole training data set. Then we can say that this is a cost function. Then the goal of the linear regression is to find the learnable parameter W that minimizes this cost function. So finally, we can say that this W star is the optimal parameter that represent that approximate our training data well, right? So this is the general process of the linear regression problem. So to understand this one deeply, let's start with the simplified one. So first of all, let's think about we only have the W1, and in this case, we have to just find out the W1, and we can define the cost function, something like this, right? Then goal is here, right? Okay, let's solve this one first. Okay, so let's think about the two flag. The left one is the FW of X, and right one is the L of W1. It means that for fixed W1, for fixed parameter W1, this is a function of the X, right? This is function of the X, or this is a mapping function of the X, or the input variable. And right-hand side means this figure represents the function of the parameter W1. Function of the parameter W1. Okay, so let's draw this figure. Okay, and then let's say we have the 3 training data. For example, like 1, x1 is equal to 1, y1 is equal to 1, or 2, 2, or 3, 3, something like that. So let's say this is a training data. Okay, so let's solve this one. Let's find out the learnable parameter W that will represent this training data set. Okay, so the first possible solution is y1 is equal to 1. So when y1 is equal to 1, the mapping function fw of x should be what? Should be x itself, right? So in this case, we can draw this straight line, something like this, right? So in this case, what is the distance between the ground truth values and the estimated values? Okay, if you think about this one, this training data set here, we can define the loss function. Loss function, something like 1/3 with 1 negative 1 square plus 2 minus 2 square plus 3 minus 3 square. So it's going to be 0, right? So in this case, the error of W1 is equal to 0, right? So we can represent the cost curve here. Cost value, something like this, right? Then what about W1 is equal to 0.5? Then the mapping function shows something like 0.5x, right? Then we can easily draw this straight line, something like this, right? When x is equal to 1, it should be 0.5, right? When x is equal to 2, it should be 1, right? Then in this case, what is the difference? What is the distance between the ground truth one and estimated one? It is something like this, right? So in this case, when W1, in this case, actually the L of 0.5 is going to be 1/3 with what about that? Yeah, 1, 2, 3, 3, right? So you'll be 3, 1/5, right? So in this case, 1 minus 0.5 squared, sorry, 0.5 squared plus 2 minus 1 squared plus the 3 minus 1/5 squared, right? So you can compute this one, right? So it will be 0.05, right, to 1, or what is that? 2.25, right? Correct? So anyway, it should be 1 over blah, 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 something like that. So in this case, L of 0.5, L of 0.5 should be here, right? Something like that. So actually, this one represents the cost, right? So if you remember previous one, we have to find the W1 that have the minimum cost value, right? So when we compare these 2 points, W1 is equal to 1 is better, right? Then the W1 is equal to 0.5, right? Then what about W1 is equal to 0? Then in this case, fw of x will be the 0.x, so it's just 0, right? So in this case, the distance will be something like this, and in this case, L of 0 is like 1 square plus 2 square plus 3 square, something like that. then it will be some kind of 4-point blah 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 things. So it will be something like this. Okay, so by searching the possible W1 in the disk space, we can draw the cost value. Looks like this, or we can consider the y1 is equal to 0.5, or the y1 is equal to 2. The cost is going to be here, right? So it means by doing similar things, we can draw the curve look like this, right? So in this case, this curve is called the cost curve. So then what I want to do is to find out the minimum we want to find out the W1 that represents this cost curve minimum. So in this case here, right? So in this case, L of 1 is equal to 0, right? So it means that W1 is 1 is the optimal parameter. Okay, so by learning this training data set, we found the optimal parameter. Oh, sorry. Optimal parameter W1 here. Okay, so this is a very simple procedure to find out our learner parameter W. Okay, so let's think about a little bit more complex one. So people keep going. Do you have any questions so far? Do you have a question? Are you there, right? Okay, so yeah, actually this this procedure is exactly brute force strategy. So we will derive the more systemical way to find out the optimal parameter W. So is there any question? Okay, if not, so let's keep continue. Okay, so from here, let's think about the little bit more complex one. When we have the W0 and W1. Okay, so it will be the linear mapping function, and we have the learnable parameter W0 and W1, and we can similarly define the cost functions like this, right? And the goal will be same. The goal is to find out the learnable parameter W that minimizes our cost function. So the W star will be our final optimal parameter, which will be the mapping function, our final mapping function, right? By the way, do you know the difference between the mean versus argmin? Do you know? Do you know the difference between them? Okay, so let's think about the example. So okay, so we have the values, the set of the values, something like 1, 2, 5, 3, something like this. Okay, so let's think about this value set. Okay, so and yes, let's say this is LW, and W will be something like. Okay, let's think about this example. So in this case, minimum. Okay, so so in this case, this one, what? Okay, let's think of the max case. Max. Actually, it's just like inverse operator. Okay, so what is the maximum values of the LW in here? 5, right? What about this? What is the values of the W that make a maximum, that make the loss function as maximum? 3, right? So please think about this one. Okay, so let's continue. Okay, so in this case, we now we have the two variable, W0 and W1, right? So W0 is here, W1 is here. Let's think about the W0 is equal to 50 and W1 is equal to 0.06. Then we can draw the straight line, something like this, right? So similar to the previous one, we can define, or we can measure the distance between the ground truth and the estimated one. It's like this, right? Looks like this. Then we can draw the figure between W0 and W1 to our loss function. Right. Then how can I draw this? How can I draw this? For example, if you remember the previous one, if the problem that we want to find out the mapping function, the straight line from the W0 to the LW, it looks like this one, the 2D plot, right? Then how can I draw this case? In this case, it should be looks like W0, W1, and LW0, W1, right? Right. Then how can I represent this one? How can I represent this cost curve in the 3D space? Actually, it's really hard to draw it, right? Then how can I represent this one? So to represent this one, we generally introduce the contour plots, looks like this. So if we draw this curve in the 3D domain, it looks like this. It looks like this. So x-axis means the W0, and y-axis means W1, and z-axis means the costs of the W0 and W1. Okay, so in this case, when W0 is equal to negative 15 and the W1 is equal to 2, then the cost function, the cost value of the negative 15 and 2 will be here, right? If we vary the combination of the W0 and W1, the cost value looks like this, right? Then what I want to do is to find out the minimum on this cross curve, right? So this is the 3D representation of the cost curve, right? So, however, as you can see here, it might be really hard to draw this one every time, right? Because this is a 3D representation. So we introduce the contour plot or the contour figure representation. So here's the things. So this is the 2D representation of this cost curve in 3D space. So this color means the cost value, the amount of the cost value. So this red values means the large loss value or the large cost value. And this blue color represent the small loss value or the small cost value. The small cost value. Okay. So by using this contour plan, we can do similar things to previous one. Okay. So now let's think about the one sample in contour plan. Let's say W0 is equal to 800 and W1 is equal to negative 1.5, right? Then we can define the mapping function fwx as a 800 plus 1.5x, right? So we can draw the straight line. Looks like this. In here, we can similarly compute the distance between the ground truth y value and estimated value. Looks something like this, right? Right. If we aggregate every possible errors among this training data set, we can compute the loss value here. Right. So our goal is to find out the parameter w, then make this loss function minimum, right? You remember, right? So let's continue. So when you think about another value, when you think about the, what is that? W1 is W0 is might be 100, or W1 is equal to 0, then the cost function, it looks like the in this case the 180. Yeah, right? So in this case, we can measure the distance between estimated one, ground truth one, looks like this, and the summation of these errors will be here, right? Then we can do similar things with the different learnable parameters w here, right? Then it corresponds to the another straight line here. Then we can find out the optimal parameter w, then make the loss function minimum. So in this case, we can also measure the distance here, the errors here. But when we pick the W0 and W1 as this one, this error will be the minimum. So in this case, our W star will be the W1, W0 and W1. It might be, I don't know exactly, but 10, for example, 10 and 0.115, right? Something like this, right? Anyway, we found the optimal solution or optimal parameter W star, something like this, right? But as we mentioned previously, it's also brute-force way to find out the learnable parameter W. Okay, so people continuing, we can think about the few possible cost function. So in here, in previous examples, we just considered the mean square error, which are defined something like this. Okay, so Ym is the ground truth output value, and Fw of Xn is the estimated one, right? Then the distance between ground truth and estimated one is measured by the square root. Mean square error, right? So this is the mean square error. Actually, the mean square error is one of the most popular cost function. Actually, in the deep learning, most of the deep learning technique, that require the regression problem frequently use this MSE rules. So we have to know that. Then actually this is the L2 norm case, or we can consider the L1 norm case. So like this. So this is the ground truth, and this is estimated one, and this is the absolute distance between the estimated and ground truth one and subjective. So this is the mean absolute error. They are also called the MSE or the MAE. So then, what are the desirable property of the cost function? What are the desirable property of the cost function? Why these cost functions are widely used? So first of all, when target y is a real value, it is often desirable that the cost should be symmetric around the zero. Cost should be symmetric around the zero, since the both positive and negative errors should be penalized equally. So let's think about, let's draw this one here. So when you think about the cost function looks like this, it might be symmetric, right? So it means that the mapping function, when we have the specific mapping function, then errors, these samples and these samples make positive errors and negative error. Xn is positive and Xn is negative. Then we have to deal with these samples equally, right? So this is the desired property of the cost function. When the cost function looks like this, it's not desirable. It's not desirable. So why? Because if the cost function is symmetric around the zero, it is easier to deal with. It's easier to optimize. So that's why we have to use the cost function that is similar to the that is symmetric around the zero. So this is a desirable one. Actually, this MSE and MAE follow this rule, right? The second desirable property is that the cost function should penalize the large mistake and very large mistake similarly. So what does it mean? Let's say there are several kinds of the samples here, and one more samples are here. What we want to do is to find out the mapping function that will approximate this major distribution of the training data set. But in some case, the mapping function is very sensitive to the outlier, right? So what we want to do is to find out this mapping function that will approximate the majority of the training data set. So this is the second desirable property. So yeah, actually, these two kinds of the cost function is not follow this second rule, right? So actually, there are several kinds of the improved one, but there is the trade-off between the statistical and computational trade-off. If we want to better statistical property, actually it was the second desirable property. In here, the cost function should be looks like this, right? So when you think about the very large error and the small error, or the another error here, the cost should be similar, right? To satisfy this second property, right? But when you think about this MSE and MAE, oh no, MAE we discussed previously, the cost curve looks like this, right? So, oh, by the way, in this case, this is the error, and this is the cost of the error, right? So, actually, these two kinds of things, the better cost function than the previous one, MSC or the MAE, is MSC or MAE, because the cost curve looks like this, right? However, it's really hard to it required more computation time to compute the cost function than the MSE or the MAE. So that's why we frequently use this simple one. But in the statistical in the statistic view, this robust cost function is better. Cost function is better. So the question is, which loss function is the best? We don't know. We don't know. Actually, it depends on the application, or it depends on the number of training data, something like that. So we cannot say which loss function is best. Okay. So this is a desired property of the cost function. Okay. So let's go back to our previous our first question. Okay. We define the cost function L of W, and L is the learnable parameter, right? Then we want to find out the F star, W star, then minimize this loss function, right? Then how can I do that? How can I do that? The first one, the thing we discussed today was the greedy search, right? The greedy search is one of the simplest optimization algorithm. We compute the cost of all possible W in a grid and pick the best. For example, okay, so let's think about this is a possible W space, right? Then we can just regularly pick the best possible, regularly pick the possible W, something like this, right? W1 or the W2 or W3, something like this. And then we can compute the loss function for each possible, okay. Let's use the superscript. W1, W2, W3, W1, and W2 or W3, right? And then we can pick the best one, right? This is actually the most easiest way to solve this problem, right? But as you know, as you can imagine, this is very brute force, right? So it's extremely simple, right? So it has too many proof to find out the optimal parameter W, resulting in the exponential computational complexity, right? So we have to think about the more systemical way to solve this one, right? So because in the real case, this number of parameter will be the several million or the 10,000 million in the deep learning area. So we cannot use the grid search anymore. So we have to think about the more clever way. It will be the gradient descent. Okay, so it will be the gradient descent. So the gradient descent, the most popular method to find out the optimal learning parameter W. Okay, so we will talk about this one next time in Wednesday. Okay. Okay, so let's finish today's lecture. Do you have any questions so far? So if 한국말로 표현하면은 뭐라고 표현할까요? 브루트포스. 뭐라 할까? 막무가내로 해본다라는 느낌인가? 뭐라고 표현하죠? 그러니까 가능한 모든 경우의 수를 다 해보는 거죠. 그러니까 우리가 그쵸? 그러니까 이게 모든 경우의 수를 다 따지는 그쵸. 그러니까 이게 뭐라고 표현해야 되죠? 그러니까 어떤 우리가 옵티미제이션 문제를 풀 때, 그러니까 사실 가능한 파서블 솔루션이 무한히 있는데, 네, 이거를 사실 우리가 모두 다 계산해보는 약간 네, 그런 거라고 보시면 될 것 같아요. 네. 무작위 대입법 모르겠네. 한국말로 뭐라고 하는지 모르겠네요. 네, 그런 것 같습니다. Yeah, here's the thing. So actually, we just passed these two loss function, the loss cost function, but comparing to this one, the equation of this loss cost function will be more complex than the MSE or the MAE. So it means that we need a much more computation time to compute the cost function. So it means that's why there is the trade-off between the statistical property and computational benefit. Okay, so is there any question? 예, 계산이 편하다. 그렇죠. 어쨌든 이제 우리가 다음 시간에 이제 그레디언트 디센트랑 배우고 하면은 사실 이제 이 코스트 펑션 자체를 미분을 해야 되는 이제 순간들이 오는데 어쨌든 이제 그 미분을 계산하고 하는 게 이제 다 그 컴퓨테이션 코스트가 되는 거죠. 그래서 이제 그 코스트를 줄이는 게 사실 트레이닝 시간을 줄이는 데도 도움이 될 거고 테스팅 상관없구나. 트레이닝 타임을 줄이는 데 도움이 될 건데 이제 딥러닝 같은 경우는 넘버 오브 데이터가 사실 거의 몇만 장씩 돌리다 보면은 사실 저 코스트 펑션의 어떤 계산량 자체가 이제 크리티컬해지는 거죠. 네. 그렇게 보시면 될 것 같습니다. 어때요? 오늘 첫 시간인데 쉽죠? 리니어 리그레션은? 여러분 다 아는 내용이죠? 아닌가요? Is there anyone who first heard about this linear regression? No? Right? Okay, so actually this linear regression is very simple, but it's really important to understand the following further concepts, something like the gradient descent or the stochastic gradient descent or the batch gradient thing, something like that. So you have to know that. You have to this concept of the linear regression first. Okay. Okay. So if you don't have any question further, let's finish today's lecture. Thank you. 그 질문 더 있으신 분들은 남아서 하셔도 돼요.